Assalamualaikum warahmatullahi wabarakatuh and good evening to all my students. In this lecture, I will explain on system of linear equations. Alright, so let's see if I have this equation. What do we call this equation? We have x to the power of 1 plus y to the power of 1 equal to 5. Okay. If you still remember types of equation, this is called linear equation. Okay, if I give you this, what is the type of this equation? This is quadratic equation. Why is it quadratic? Because the power is 2. Alright. And this is linear because the power is 1. So this is linear, this is quadratic. Alright. So if we have one equation like this, we call it linear equation. If we have another equation such as 2x plus y equal to 10. Okay, the first one is x plus y equal to 5. And we have more like y equal to 2, for example. Alright, now how many linear equations that we have here? We have 3 linear equations. Okay, when you have more than one linear equation, okay, we say this as a system of linear equation. Okay, so this is what we are going to learn today, where you can transform, okay, your system of linear equation into matrix. Okay, so linear equation form can be transformed into matrix form so that you can solve all the real life application of involving the matrix. Okay, so this is what the most of the software do when you solve a real problems. Okay, so in real problems you won't have just one problem, right? You won't have just a linear equation, but you will have a system which consists more than one. It can be 100,000 and so on. So this is the purpose or the application of where we apply matrices, okay, to solve our daily life problems. Alright, but first, before we go to the application of the matrices, let us know first type of linear equation. Okay, I'm sorry. Correction to my previous words. It is not type of solution. It is not types of system of linear equation, but it is types of solutions to system of linear equation. Right. So types of solution, there are 3 for a system of linear equation. So the first one is system with infinitely many solutions. Okay, so it means here the unknowns in your system of linear equation can take many values. Okay, so we will look at that later. The second one, a system with a unique solution. It means that the unknowns in your system, okay, can only take one value. Okay. The third one is system with no solution. So there is also a system of a linear equation where it cannot be solved. There is no solution for that system. Alright, so we will look at all these three types of solution in the previous slide. Right, so a system with unique solution. Okay, I'm sorry because it didn't follow the order that as I mentioned in the previous slide. Alright, but there are three, so it doesn't matter. Alright, so the first one, let us go with a system with unique solution first. Okay, so let's say you have two linear equation here. Okay, you have two linear equation here. So since this is a system, this is more than one linear equation, so we call it system, okay, of linear equation. Alright, so we can transform the form, this form, okay, which we write it in a equation, okay, in the form of equation. We can transform this, okay, we can write this into augmented matrix as written here. Okay, so this system is consists of matrix. Okay, what is the scalar for x1? It is 1, okay, so 1. What is the scalar for x2? It is 3. What is the scalar for the second equation of the x1 here? It is 0. And for this one, it is -2. Okay. And what are the unknown involved? It involved with x1 and x2. So write it x1, x2 in one column. Okay, so the equation will be equation like this, equal. Okay, and then create another column for the solution, which is 4, 1. Okay, you see, so this is matrix A. This is capital X to represent x1 and x2, equal to, what is this? This is the B. Okay, equal to B. Alright, this means we multiply matrix A with the X, it will be equal to B. Alright, so when we follow this, 1 multiply with x1, you get x1, plus with 3 times x2, you get 3x2, equal 4, because you are multiplying A with X, and this is the first row. So this is your first equation. This is second equation. Okay? Right. So this is the matrix form of your linear equation. Alright. So since you only have two unknown, alright, two equations, so you will be dealing with 2 by 2 matrix. Alright, and then to solve for this equation, you can write it in the augmented form. Okay, when you write your matrix A, okay, next to your matrix B, okay, in the square bracket like this, and you separate your matrix A and B by using the straight line here. Okay, this is called augmented. Okay, when you write two matrices in one close bracket like this is called augmented matrix. Alright, so when you solve for this, Or you can, without writing in the matrix form, you can know the solution already, right? Where you can solve for this. Okay, but since this is a system, okay, and we want to apply the matrices, so we still need to write in the matrix form like this. Alright, so from here, this system has a unique solution, because if you solve for x2, x2 is equal to negative 1 over 2. And when you substitute x, they swap the solution here. This is x2 and this is x1. Okay, when you substitute x2 into your first equation here, okay, you will solve for x1, where x1 is equal to 11 over 2. Okay, so this is called unique, because for particular unknown, which is x2, okay, it must equal to negative 1 over 2. And x1 must equal to 11 over 2, so that it can satisfy both linear equation here. Okay? Understand? When you only have one solution for one unknown, that is called unique solution. Alright, so you cannot change the value of x2 here to be some other number. Okay, because it won't satisfy these two linear equations if you do that. Only x2 equal to negative 1 over 2 and x1 equal to 11 over 2 will satisfy this equation and this equation. Okay, so this is what we call a system that has a unique solution. Alright. Okay, now we move to the second type of solution, where this type of a system has infinitely many solution. Okay, so how does system of linear equation looks like if has infinitely many solution? Okay, your system will be looking like this. Okay, so when you have first and second linear equation, so this will create a system of linear equation. Okay, but if we look at your second linear equation, okay, both of your unknowns x1 and x2, they are all 0, including the right hand side. Okay, they are all 0. So when you write this equation into matrix form, you will have like 1, 3, 0, 0. This is your matrix A. And your unknown is still x1 and x2. Okay, which is equal to the right hand side, which is 4 and 0. So this is your x, okay, capital X, which is equal to B. So this is a matrix form, and you rewrite this into the augmented form, okay, where you separate matrix A and matrix B with a straight line. Okay, so since we know this is all 0, so we can only solve for the first linear equation. Okay, if you have this, the first linear equation, if you take the 3x2 to the right hand side, so you will have a linear equation like this. Okay, so this type of a system linear equation, x1 can be anything, it can take any value, okay, depending on the value of x2. Okay, so any value, okay, of a real number. So your x here can take any real value. Okay, so x1 will depend on your x2. If you choose your x2 to be 0, okay, if x2 equal to 0, your x1 will be 4. Okay, so if you can also do alternate way where you can solve for x2 and substituting your x1. Alright, so if your x2 is equal to 1, what would your x1 would be? So x1 will be 1. Okay, and the list will continue infinitely. Okay, this is what we call a system with infinitely many solutions. Okay, so any numbers for x1 or x2 can satisfy this equation. Okay. Okay, and the last type of solution is a system with no solution. Okay, this is how a system with no solution looks like. Alright, so if you look at the two linear equation here, the first one is normal equation. It looks normal. Alright, but look at the second equation here. Okay, so 0x1 plus with 0x2 suddenly can be equal to 2. Alright, so it is impossible for this kind of equation, right, which the unknowns are 0 suddenly equal to some number. Right, so this is a system that we call has no solution. Alright, so when you look at your equation, system of linear equation, when you look at this, you have 0 for your unknown, okay, for your unknowns, okay, and it equal to some number at the right hand side. This is a sign of a system with no solution. Alright, so rewrite this into a matrix form. This is 1, 3, 0, 0, and your x1, x2 here is equal to 4, 2. So this is matrix A, matrix X equal to matrix B. And we write this into augmented form. Okay, you will have this. Alright, so you might be wondering, when you transform your matrix into augmented form, where is the x1 and x2 here? Okay, x1 and x2 is located in here. Okay, so this is where x1 and x2 are when we write the matrix in the augmented form. Alright, so you can see clearly that your x1 plus 3x2 equal 4. Okay, and 0 of x1 plus 0 of x2 equal 2. Okay, so same goes to the previous one. Okay, it's just that I forgot to explain where is x1 and x2. Your matrix x when you write in the augmented form. Okay, so we didn't write this when we write augmented form. But you must know that x1 and x2 or other unknowns are in a column. We write it in a column. Okay. Alright. Okay. when we have a problem, we will model our problem with an equation or with a few equations. Okay, and then we will determine the unknowns of our problem. Alright, so when it involves with unknowns, it will become our interest to solve for our unknowns. Alright, so in matrices, once we transform our system of linear equation into matrices, okay, there are four methods that can be used to solve system of linear equation. Alright, so the first one is the inverse of the coefficient matrix. Alright, so we have learned the inverse matrix before, right? Which is E inverse is equal to 1 over the determinant, okay, times the adjoint. Okay, alright, so we will use this inverse matrix and solve our equation matrix AX equal to B. Alright, so this is our unknown, right? So if we want to solve for our X, A, we bring it to the right hand side, it will become A inverse times B times matrix B. Okay, so this is where A involve apply. Alright, so this is the first method, the inverse of the coefficient matrix. Alright, so the second one is Gauss elimination. Okay, the third one is Gauss Jordan elimination. Alright, so Gauss elimination and Gauss Jordan elimination will apply ERO method. Okay, elimination, elimination row operation. Okay, so we will use ERO method, okay, to apply into Gauss elimination and Gauss Jordan elimination. Right? Gauss Jordan elimination is the continuation from the Gauss elimination. Alright, so I will explain more on these two methods in the next slide. Alright, so the last one that can be method that can be used to solve system of linear equation is Cramer's rule. Okay, Cramer's rule use determinant matrix. Okay, determinant of a matrix. Okay. Right, let's go to the first method of solving system of linear equation, which is the inverse of coefficient. Right, when we have equation system of linear equation that consists of few linear equations, alright, you can write it into matrix form. Okay, you can have matrix A and X is your unknown. Well, this is your matrix B. Alright. So now X will become our interest. So X will become our subject here. When we rearrange this equation, okay, so that our X become a subject, A will become, when we take A to the right hand side, it will become A inverse times with matrix B. Alright, so where A inverse, we have learned before that A inverse is equal to 1 over the determinant A times the adjoint of matrix A. Okay, and then you multiply with B, you will have a solution for your unknown. Let's go straight to the example. If you have a system of linear equation like this, okay, you have 1, 2, 3 linear equations. So you will, and you have 3 unknowns, which is X, Y, Z here. So 3 equation, 3 unknowns, means you will have 3 times 3 matrix. Alright, so let us rewrite this into matrix form AX equal to B. So what is matrix A? So you just take the coefficient of your unknown. Okay, so if you look at here, the first equation, you have 0 for X. Okay, and the rest are okay. So the first unknown, which is X, this is column for Y, this is column for Z. Okay, so right for X is 0. What is Y? Coefficient of Y is 8. Coefficient of Z is 6. Okay, so second row, second equation, minus 2 for X, 4 for Y, minus 6 for Z. Alright, and the third equation, you have 1 for X, 1 for Y, and minus 1 for Z. So what is your unknown here? You have 3 unknown, X, Y, Z. Okay, and this is equal to your B. The right hand side is minus 4, 18, 2. Right? So we have our matrix form. Once you have write your system of linear equation into matrix form AX plus equal to B, now you can determine that your A is this is your X, and this is your B. Right, so you have your A, X, B. Okay, next, remember we want to solve this system by using the inverse matrix. Alright, by using the method of inverse matrix. So we know that our AX equal to B. When we want to solve for our X, A will we take A to the right hand side, it will become A inverse times with matrix B. Alright, so we have B, matrix B. We have matrix A, but we do not have A inverse. We do not have inverse matrix A. Okay, but we can calculate inverse matrix A, okay, inverse of matrix A by using the formula 1 over the determinant of matrix A times with the adjoint of the matrix A. Okay, if you can still remember, we have two methods to find the determinant. Alright, the first method is by add and two additional columns, okay, two extra columns at the back of your matrix. Alright, and then you need to multiply all the diagonal part, okay, subtract with the diagonal part on the opposite direction. Right? And then the second method is by using the minor cofactor. Minor cofactor method by expanding row or column. Okay. While for the adjoint, you need to find the minor, then proceed with cofactor, and then transpose your cofactor. This will give you adjoint of matrix A. So these are the flows. Okay. Right. So I didn't want to show you again and again on how to calculate the determinant and find the adjoint. So I have told you the flows. Alright. So I leave for you as an exercise. Okay. For you to recall on how to find the determinant and the adjoint. Okay. But here I have already calculated the determinant of matrix A is equal to 50 and the adjoint is equal to this matrix. Alright. So substitute these two values into the inverse formula. Alright, so this is the inverse matrix A. Okay, so the next step is you need to multiply this in A inverse with B. Okay, so solving for x, what is our x? Our x consists of unknown x, y, z. Alright, so this is inverse matrix A times with your B. Alright, so you do one by one. Alright, you can leave your 1 over 50 first, okay, and solve for the matrix first. Okay, remember how to multiply? Minus 1 multiply with minus 4. So minus 1 multiply with minus 4. Plus with minus 7 multiply with 18. Plus with 36 times 2. Okay, and then go to the next row. 4 times minus 4 plus 3 times with 18 plus 6 times with 2. Alright, so we're done with second row. Now go to the third row. 3 times minus 4 plus minus 4 times 18 plus minus 8 times 2. So when you solve this, you will get minus 50, 50 minus 100. Okay, so 1 over 50 times with minus 50, 50 minus 100, that will leave you with minus 1, 1 minus 2. Okay, which is this. Right, so here the solution is x equal to minus 1, y equal to 1, z equal to minus 2. Alright, so we're done with inverse method. Now we go to the second method, which is Gauss elimination method. Right, so same first uh, first step as inverse method. You need to transform your system of linear equation into matrix form. So from here, you determine what is your matrix A, what is your unknown, and what is your matrix B. Alright, and then you write your matrix in the augmented form. Okay, matrix A next to the matrix B. Okay, right, writing your matrix in the augmented form will give you a solution for your unknown. Right, so as I have mentioned before previously, that in Gauss elimination method we will use elementary row operation. Okay, so you will apply ERO in this method. Alright, so the idea is you need to reduce this to REF or upper triangular form. Okay, if you forget what is REF form, okay, please refer back to the lecture types of matrices. Alright, but basically REF form is you reduce your matrix. Your matrix would be a diagonal one, and the bottom part will be all zero. Okay, this is REF form. Okay, the bottom part elements are all 0, and you have a diagonal 1. Okay, that is REF. While RREF is basically mean identity matrix. Okay, this is right. So the idea now is to reduce matrix A here to REF matrix, REF form. Alright, so your matrix A should look like this. Oh, what an ugly matrix. Okay, so throughout this process, to reduce your A in the form of REF, it will involve with ERO. Okay, where elementary row operation will reduce the whole row, including your matrix B in this side. Okay, so automatically when you apply ERO, B will also change. Okay, right. So we go to the next slide. Okay, for this example, okay, we're still using the same example. Okay, so it is to show we're using the same example for the purpose to show you that no which no matter which methods you choose to solve the system of linear equation, you should get same answer. You should get the same answer. Alright. So once again, we write our system into matrix form. So it is a 0, 8, 6, minus 2, 4, minus 6, 1, 1, minus 1. That is your A. And your B, your X consists of X, Y, Z. These are your unknown. And your matrix B is minus 4, 18, 2. Okay, so this is A, this is X, this is B. Okay, so next step, you need to rewrite your matrix into augmented form. Okay, so write your matrix in the augmented form. Right, this is your X. You solve for your X. This is your matrix A, remember? Okay, so separate with straight line for matrix B here. Okay, so our aim is to reduce matrix A to REF form. Okay, so our aim is to make this become 1. This should be 1. This should be 1. While the bottom element must be all 0. Must be all 0. Okay, so we will apply ERO to the augmented matrix. Alright, so remember when we use ERO, there are 3 characteristics, okay, main characteristic that we can apply. Alright, which is multiplying the scalar, interchanging the row, and plus minus the row. Okay, look. The first step is to reduce the first element 0 here to 1, right? Okay, so since this is a 0, what we can do to make this one, the easier way is to interchange row 3, interchange your row 3 to row 1. Okay, and row 1 change to become row 3. Okay, when you do that, it will involve the whole row. Okay, interchange the whole row. Look at here. Okay, so row 1 here, the whole row, write it as a third row. So all the element in the first row become the third row. 0, 8, 6, including the B, which is minus 4. Okay, clear? Alright. Then replace the element in the first row by the element in the third row here. Okay, so replace it here. 1, 1, minus 1, including 2. Okay, clear? And don't do anything to your row 2 because row 2 does not change. We only interchange row 3 with row 1. Okay? Okay, so next our aim is to reduce minus 2 here to 0. Okay, what should we do in order to reduce this to 0? Okay, so we want to interchange row 2. How? We can use row 1 to help us to reduce row 2. Okay, so we can plus with 2 row 1. Okay, because if we do this, row 2 is minus 2, 4, minus 6, 18, right? And we multiply scalar 2 to row 1. Row 1 multiply with 2. So 2 times 1 is 2. 2 times 1 is 2. 2 times minus 1 is minus 2. 2 times 2 is 4. Okay, so to make minus 2 become 0, we must use operation plus. Okay, so by plus, perform the operation addition to this row, you will get 0 here, and the rest doesn't matter. You just solve it. You just solve it. Okay, 4 plus 2 is 6. Minus 6 minus 2 minus 8. 18 plus 4, 22. Okay, so we go to the next slide. Look at what happened to our row 2. Right, so this is what we get when we perform ERO R2 plus 2R1. Okay, alright, so next step is, since our third row, the first element of our third row is already 0, which is our aim. So we can skip this one and move to the next element, which is this. Okay, our aim now is to reduce this to 1. Remember, this is the main diagonal, so make it 1. Reduce it to 1. So how to reduce this element to 1? We can multiply R2 because this is row 2, right? So we multiply scalar 1 over 6 to R2. It will reduce 6 to 1. Okay? So it will involve the whole row. This whole row will you need to multiply with 1 over 6. 1 over 6 times 0 is already 0. 1 over 6 times 6 is 1. So 1. 1 over 6 times minus 8, that will give you minus 4 over 3. 22 over 6, that will give you 11 over 3. Right, so we're done with this element. Next, what is our target? Our target is to reduce 8 to 0. Okay. So in order to reduce 8 to 0, okay, where 8 here is in row 3. So row 3 will change. Okay, and we can use row 2. Okay, we can use row 2. Sorry, this is a mistake. It is 8 row 2. Okay, minus 8 row 2. That will reduce your 8 to 0. Okay, so row 3 is 0, 8, 0, minus 4. This is row 3. Then we minus with 8 row 2. So row 2 is here, which is 0. Times with 8, you get 8. Minus 4 over 3. You times with 8, that will give you 32. Minus 32 over 3. Hmm. Hmm. Sorry, this is 6. My mistake. Alright, and then 11 times 8 is 88 over 3. Okay, so you minus, this will give you 0, this will give you 0, this will give you 50 over 3, and this will give you 100 over 3. Right? What time is 12? Yes. Right, so this transfer this to row 3. Alright, we're almost done. One more left, which is this. We need to reduce this to 1. Okay, because our aim is matrix A must be diagonal, mean diagonal here, and the bottom part should be 0. So we have 3 elements here, which is 0. Now this diagonal element also has reduced to 1 here, 1 here, and we need this to be from 1 as well. So to reduce element to 1, just multiply the scalar to that row. Okay, so row 3 or the element in row 3 we multiply with 3 over 50. So it will reduce the matrix to this. Right. So next what we do is we must rewrite the equation back to system of linear equation. Okay, so this is our REF matrix. Okay, REF form. We have all the main diagonal, diagonal 1 here. Okay, and the bottom part, the bottom elements are all 0. Alright, so we must rewrite this matrix into system of linear equation in order to solve for our unknowns. Okay, so our unknown is x1, x2, x3, remember? Okay, so in the augmented form, remember before this I said the first column is for the first unknown. The second column is for the second unknown. The third column is for the third unknown. And this is your B. Okay, so to rewrite this, okay, we write the first row first. X1 times x1 is x1 plus 1 times x2 is x2. Okay, plus with minus 1 times x3, it is minus x3. Equal to what? Equal to 2. Okay, then go to the second. We have none for x1. So 0. We don't need to write it. Okay, so 1 multiplied with x2. x2. Okay, plus with minus. So we just directly write minus 4 over 3 x3 equal to b is 11 over 3. And the last row, we have none for x1 and x2 because they are 0. We only have for x3. x3 equal to minus 2. Okay, so one of the unknown already solved. Okay, so x3 we know is equal to minus 2. We can substitute this into the second linear equation here and we can solve for x2 where x2 is equal to 1. Okay, now we have x3 and x2, so we can solve for the first linear equation. Okay, substitute value x2 equal to 1 here, 1. Okay, x3 equal to minus 2, so it will become 2 here. Okay, so x1 equal to 2 minus 2 minus 1. So x1 equal to minus 1. So solve. Alright, so that is Gauss elimination method. Reduce it to REF form.